Are we sure? All right. So today we're going to talk about Kepler's laws of planetary motion. But before we do so, I always like to review from what we have been doing. So the whole topic that we're talking about is astronomy. Your first test will be next Wednesday. Your first test will be next Wednesday. It is on astronomy, so everything that we cover. So today we'll talk about Kepler's laws. Tomorrow we will touch on the planets. And then Friday we'll talk about the moon and tides. Monday the sun. Tuesday we'll spend reviewing and playing catch up. And then Wednesday will be your test. Okay? All right. So Monday, what did we talk about? The Big Bang. And what's the Big Bang? Okay, so started off as a single point. There was an explosion, and then it expanded. That's what the Big Bang says. Okay, then we talked about red shift, blue shift. Red shift goes what direction? Away. And so that means the wavelengths get what? Longer, right. Okay, blue shift comes which direction? Towards us, so that means the wavelengths get shorter, right. Then we talked about the nebula. What's a nebula? We talked about the nebular theory. A gas cloud, big ball of gas, okay? Yesterday, what did we touch on? Something I told you that I always forget and mix up. Rotation and revolution, very good, Jaden. Okay, so rotation is equivalent to what? The day, 24 hours, okay? And a revolution, 1 whole year. That was the big piece from yesterday. And then you had to complete a card sort on it. Does anybody have questions so far? Make sure you ask questions if you have them. And it's better to ask them sooner than later, okay? All right, so today we're going to talk about Kepler's laws of planetary motion. There are 3, but we're really just going to talk mostly about the first 2. I will go over the third one, but the first 2 are the most important for you. Okay, so Tycho Brahe was a Danish astronomer. He had an island observatory and the best measurements of the positions for all of the planets and the moons. Okay, Mercury, Venus, Mars, Jupiter, and Saturn. The next we're going to talk about, and he is the one that we're going to talk about the laws, Johann Kepler. And Johann Kepler was an Austrian mathematician. Okay, so you think mathematician, right? But we're talking science. So he was interested in how the planets moved around the sun. So he went to Tycho's island in order to get actual accurate measurements. So at that time, many astronomers believed that the planets orbited around the sun in a perfect circle. So they thought that the circle was perfect and that's how it orbited. Tycho, his accurate measurements for Mars didn't fit a circle. So Kepler found that the orbit of Mars fit more like an ellipse. And yesterday we talked about the Earth taking a specific shape. And what did the Earth look like? So like a squished circle, right? Okay, so the equator was a little bit longer compared to the poles, right? So that's what we talked about yesterday. So an ellipse is really like an oval, takes on an oval shape. So what is an ellipse? Okay, it's a geometric shape that has 2 foci, so 2 focal points. A circle only has 1 central focus because it's in the middle of the circle. So in an ellipse, you've got 1 on either end. So the way that we like to look at it is that it has a major axis and a minor axis. Okay, so the major axis would pair up with what? What did we talk about yesterday that goes this direction? The equator, right. Okay, and then the minor axis is going to, instead of being horizontal, it's going to be, right, which is going to be what? Vertical, right, very good, okay. So, there's what is known as the perihelion and the aphelion, okay. So these, the perihelion is when Mars or any other planet is closest to the sun. So you see that on the left-hand side, okay? The aphelion is when Mars or any other planet is farthest from the sun. So it's on the opposite side. So perihelion over here, the aphelion over there, okay? Any questions so far? So the second thing, I'm sorry, we can't see it. Okay, the second law of planetary motion, the line of planets to the sun sweeps out, okay, and they're equal areas at equal times. So as the planet actually travels around the ellipse. Okay, so Kepler, Johann Kepler, he found that Mars changed speed as it orbited around the sun. So it was faster when it was closer to the sun. So the closer it was, the faster it moved. And then it was slower when it was further away from the sun, okay? So areas A and B, swept out by a line from the sun to Mars, were equal over the same amount of time, okay? Does that make sense? So faster when it was closest to the sun, and then slower when it was further away. So Kepler found a relationship between the time it took a planet to go completely around the sun and the average distance from the sun. So we said that he was a what? You see a lot of what up here? Math, right? So he's a mathematician. So the relationship between the time it took a planet to go completely around the sun and the average distance from the actual sun. So the third law, and this one we're not going to get too in depth on because this has a lot of math. This is the ratio of the square of revolution time for two planets is equal to the ratio of the cubes of their semi-major axes, which we saw, if I go back, at the bottom. Because you've got your major and minor, and then at the bottom there's what is known as the semi-major axis, okay? So Earth's year is 1 year, and Earth's semi-major axis, the distance from the Earth to the sun, is considered 1 astronomical unit, and we label that AU. And then if you look down here, we've got this big long formula, okay, because it can be seen multiple ways. So we've done different types of math in here. This is just ways of flipping the equation. So this one we're not going to be too concerned about, okay? So pretty much though, if you know the distance from the sun and the year of planet A, and you know the distance from the sun for planet B, you can find the year of planet B, because you're essentially doing cross multiplication, okay? Or if you know the distance from the sun and year of planet A, and you know the year of planet B, you can find the distance from the sun for planet B. So if you have at least 3 pieces, you're able to find the 4th piece. Any questions? So up here, this is the orbits of the planets. And if you look at them, a lot of them are pretty close. They're pretty equal. So Kepler's laws apply to any celestial body that orbits any other celestial body. So any planet around the sun, the moon around the earth, any satellite around the earth, the International Space Station, and any rings around any planet. Does anybody have questions? Kepler's laws are confusing, but we need to focus on 1 and 2.